Welcome back, everyone. We're at 3.4, halfway through chapter 3. We've got some more interesting things to look at. Remember, zeros, solutions, all that stuff? We're going to take it to another level. Not too far above, but we will improve on what we already know. So, talk about quadratic functions. Remember, we're talking about this guy and all its relatives. And more generally, if we put a number in front of it, a coefficient. Now what this says is, if we look at this original one, we'll call it the basic one. That one is sort of what it looks like. You know what it looks like. If the number in front is bigger than 1 in absolute value, in other words, positive 1, negative 1, it's further away from 0. Then it's stretched vertically or narrow. So if we have 2x squared, what we'll have is something that is more like this. If we have something like minus 2x squared. Rather similar. It does the same thing as this, except that it's inverted. So because of the negative sign, it'll be narrow, but like that. So that's if you have something greater than 1 or less than negative 1. Now what about the fractions? The ones on the number line, here's 0, there's negative 1, there's positive 1. Anything in here is what we're talking about by this 1 having its absolute value less than 1, greater than 0. What that does is, let's get the basic one back here again, a little bit better this time. So there's the basic one. X squared. Now let's pick something in between. We're going to do something very similar. So there's x squared. What happens if you have 1/2 x squared? Well, that says the graph is going to be shrunk or compressed, making it wider. So this one, if you compare the two, is going to be like that. And that's because the 1/2 makes the y values rise slower. If we have minus 1/2 x squared, the same sort of thing happens, except because the minus sign is inverted, so it would look something like that. There, and there, and there, and there, and of course, we ought to fix this too, right? Okay, next. Now, you can look at some of the other things. If you get a straight, then if, let's see, make sure it's, okay. So, compared to ax to the n, if you get a minus sign, or put a minus sign in front of the regular one, it's going to reflect it across the x-axis. What's that mean? Whatever you have on the top is going to be on the bottom instead. It'll be flipped. It'll be flipped. A mirror image across the x-axis. So for example, this would turn into that with a minus in front of that. And if you have this to begin with, then you end up with one that looks like that instead. Whichever way it is, whichever side of the x-axis it is, it's going to be flipped. Next, that's the reflection, because that minus sign in front of here. Next, the graph of f of x, and here we've got this basic one, and what we're doing is we're adding a number out here. And if the number is positive, it moves it upward. If it's negative, then it's going to move it downward. So what's that mean? Here's your basic one, and let's call this x squared. What does x squared plus 5 look like? Well, it's going to move it up, similar to this. So the k being positive moves it up. If we have a minus 5, instead of moving this one up, it moves it down, so it'll look like that instead. It's sliding down or sliding up according to whether this number out here is positive or negative. Number 2. Number 3. Another thing that will change the basic function is if inside, if instead of the x, we have x minus something, it's going to translate it left or right. If h is positive, you move the original one like this. If h is negative, you move it like that. Now this can be a little bit tricky. So here's my x squared, just for a quick example. So there's the original. If we have h positive, then we're going to be moving it out like this to the right. If h is negative, it will be just the opposite. You'll move this original one out over here. It'll look like that. And this fourth one is a combination of all those put together. The A is going to determine whether it opens upward or downward. The K is going to determine whether you move the basic one upward or downward. And the H in here, as long as you have this minus here, then it's going to move it left or right. Now, to be honest, that is a little bit tricky because of that minus sign. So what I do is I look at whether this is a plus or minus here. Put the H there. If I see a plus number, like an x plus 6, I move it this way. Just the opposite way of the sign or operation between the x and the constant. If instead I have x minus 6, and now that's squared, I take the opposite of this, and the original basic function is moved to the right. You can practice with some of these using your graphing calculator. That's one of the beauties of having a graphing calculator. You can make these changes and just play around with it to your heart's content. You can start with this one. In fact, some of you might have one that is a color version. So you might go to the y equals key, type the x squared in, hit the graph, and take a look at it. Then go back to the y equals key again. This time, instead of y1, slip down there to y sub 2 and put in a different one. So for example, if we look at that last one, maybe we would have a negative 2 and then x minus 3 squared plus 5, let's say. Now what's that going to do? First of all, the x squared, you know, would look like this. But the minus 2 is going to do two things. First of all, the minus means this is going to be inverted. It's going to be turned upside down. The 2 means it's going to be rather skinny. or pulled vertically. The 5 means the basic look like this, the basic look like that is going to be moved upward. The whole graph is going to move upward 5 units. And this number in here is the one that's going to move it left or right. And the way I keep it straight is, if it's got a -3 here, I'm going to be moving to the right. If it's got a plus, like an x plus 9, that's going to move it this direction. You do it what way you need to so you can keep all of these things straight. You've got several different things that can happen. You could have a minus or a plus here. This could be greater than 1 or less than 1. This will move the basic function left or right, and this moves the basic function up or down. So let's take a look at this one. First of all, let's put this together. First of all, this, the x to the 5th, is an odd exponent. Being an odd exponent, its basic look is going to be like the cubic function. Now, because this isn't 3, it's a higher number, it's going to be flattened somewhat in the middle here where it crosses the origin. The important thing is, if this is an odd number, it's going to be going up to the right and down on the left. Now, if there's a minus sign in front, remember that's going to turn it upside down. So minus x to the 5th, instead of going up to the right, it's going to go up to the left instead. Instead of going down to the left, it's going to go down to the right. In other words, it's flipped on the y-axis because of that minus sign. So that's one thing. Now this is a plus x to the 5th, so this one's going to start out looking like that. But it's got a -2 at the end. That means you're going to take this graph and you're going to move it down 2 units. So you end up with something that'll look like this, because you're moving it down 2. Something like that. And notice that the function's increasing everywhere. So if you take a look at this, if you were here on the graph and you're moving to the right, every time you take a step, the y value gets higher. And not only that, but it's going to approach infinity as you go to the right. And there's a better looking graph than the one I created, but I hope you got the idea. Notice that something that I mentioned, because x to the 5th is a higher power than x to the 3rd, this part right here is going to be flattened. Because the basic function is x to the 3rd, because we've upped the ante on the power, it's going to flatten the part right in the center. How about this one? Well, how about pausing and see if you can make a guess at this one and come back. All right, let's suppose you took that guess and you look at that and you say, oh, let's see. There's a 1 here. So this original is pretty much the same. It's not skinnier, it's not wider. What else do I see? I see that it's x, well, I see that it's to the 6th power, that's even. That means that it's going to go up to the left and up to the right. Because it's 6 instead of a 2, it's going to be flattened a little bit at the bottom. The higher this number is, this even number, the more it's going to be flattened near the origin. So we're getting close, but we haven't taken this into account. Now remember, inside the quantity like this, where the x was, it moves it left or right. Since this is a plus 1, it moves it to the left. So we'll take this one and we'll move it to the left 1 unit. Make sense? Shape is the same. It's not inverted because there's no minus sign. This moves it left. This means it goes up to the left and up to the right like an x squared does. And since there's nothing out here, you don't move it up or down. Again, a little bit of a picture. There's our picture. It goes up on both sides, just like x squared does. Because it's x to the 6th, it's flattened on the bottom here. And because of plus 1, it's moved to the left 1 unit. Next, how about this one? We've gone through a couple of examples. If you didn't pause before, try it again. It's not too difficult. See if you can do it. All right, you're back and you're ready to go. So we're going to have 4 possible changes. It says x cubed. So what's our start? Our start is cube looks like this graph. So that's the start. First change is there's a minus sign out here. That means that it's going to look like this instead. Turn that upside down. Next thing, there's a 2 there. That means it's going to be narrower. So instead of this, it's going to look more like this. Try to make that narrower. Next, it has a minus 1 here, so that's going to move it to the right 1 unit. So we're going to take this and move it to the right 1 unit. And then I'll show that later. This plus 3 means it's going to go up 3 units. So to the right 1 unit and up 3. And we'll get a good picture of it. There we go. That's a good one. Notice that's moved over 1 and it's moved up by 3. And notice also that it switched from this looker up here, it switched left to right, so it goes up on the left, down on the right, instead of vice versa. Now here's some really good news. We've talked about domains before. That's the possible x's you can use for a function. What is the good news? Well, polynomial functions, that's where you have exponents of the x that are integers, positive integers, 0. The good thing is that they're going to be smooth, no jagged edges. They're going to be continuous. If you're going to draw them, you don't have to lift your pen. And it's going to go from negative infinity to infinity. The range depends on whether it's even or odd. If it's odd degree, then you're going to get all real numbers for the range. If it's even, then it's going to depend on where it starts and where it stops vertically. Okay, I think that's about it. Oh, here we go. One more thing. These graphs also say that if it's odd degree, now remember what the odd degree looks like. I'm just going to draw one simple picture. One of the basic odd degrees is the cube function, so we'll take that just as an example. If it's odd degree, notice it has to go through the x-axis. It has to. If you move it right or left, it's still going to go through the x-axis. Move it up or down, it's still going through the x-axis. Squeeze it, flatten it, it still goes somewhere through the x-axis. And that's what this means. If your function is of odd degree, then there's some number some x that makes f of x equals 0. In other words, it crosses the x-axis, because this one gives you a point x, 0, which is on the x-axis. Hope you can read that. And you can take a look at that. If you can factor it, you can see where the x-intercepts are. You get the zeros, also known as the x-intercepts, by looking at the factored form. If you've got a function, for example, and we're just going to put part of this. So you've got some factors here, and you've got some more. And if this one, for example, is x minus 7, set that x minus 7 equals 0. That means one of those x-intercepts is going to be at x equals 7. It's a root, it's a solution, it's a 0. All three of those are different manifestations of the same thing. So we're going to have a bunch of pictures this time. Here's an example. Notice this is an x cubed. So it looks like on the extreme right and the extreme left, it looks like the cube function. If you ignore this middle side, middle part, it looks like a cube function. Now the 2 being here means this is stretched. This climbs faster and descends faster. And then the extra terms, the other terms, are what create the interesting characteristics that go between the right and the left. Over here, remember, we're still talking odd degree. If you look down here, you've got a minus x cubed, so the x cubed function is turned upside down. And if you look at our factored form, you see that it's going to cross at 2, and then something weird, cross at I and negative I. Well, you can't see those on the real number line. So this is the only x-intercept. These will be, we might say, in Never Never Land, okay? Just like this one over here. In factored form, this tells us we've got x-intercepts of 1, negative 2, negative 3, which you can see right above here. On the third one, we've got an x to the 5th, and it's a positive out here. So on this extreme side and this extreme side, it resembles the x cubed function, or the cube function. And in factored format, you can see that you're going to have an x-intercept at 1, and that's this. And you've got three x plus 2's. Well, you can only have a negative 2 at one place. So because you've got multiple ones, you have not only it passes through, but it intercepts as well. That was the odd. Here's the even. The range will be a form like this, depending on what that k is. Remember what the k is? That's your k right there. And that's going to determine what the range is, whether it goes from here on up for the range, or whether it goes from here down for the range. Remember, the range is y values. Now, behaviors. The behavior of a graph at 0 depends on the multiplicity of the 0. At a 0, not at 0. So it depends on the exponent. The graph crosses at C0 if C has multiplicity of 1. So if there's only one of these, then it's going to cross the x-axis right there. If it has an even multiplicity, if you've got x minus c factored, and this is a 2 or a 4 or a 6 or any even one, then it's going to turn at c. It'll turn at c. Now, it might be turning from going down to going up, or from going up to going down, but it's going to turn around at c. And it's going to be tangent to the x-axis at c0, or factor of x minus c, if the multiplicity is greater than 1. It wiggles at c. In other words, it does something like this. It doesn't keep on turning, it makes an abrupt change. Notice also, because of this wiggle at c, either it's going to continue to increase as x increases, or it's going to continue to decrease as x increases. And odd degree and even degree, you can see that the polynomial functions have turning points where it changes from increasing to decreasing, or decreasing to increasing. Turning points. If you've got a polynomial of degree n, at most, it'll have n minus 1 turning points. So if it's degree 5, for example, it might have at most 4 turning points. The end behavior. Well, this is a nice one. This is really easy. The end behavior depends on if you've got these in order, these terms in order of x's, x powers of x, decreasing. All you have to do to find out what the end behavior is look at that first term. And that's going to tell you. The end behavior is going to be determined by the power of x of that leading term. If it's an odd one, then on this side it's going to look like this. On this side it's going to look like that. Now, there might be some strange things going in the middle, but we're talking about just the end behavior. If it's an x squared, then it's either going to be like this or like that. And of course, this can be turned upside down too, but that's the basic look. So take a look at this one. Here we've got a function. This is our leading term. It's x cubed. Now, these terms out here are going to make some things happen in the middle, but for end behavior, you don't even have to worry about the 2. Since it's a positive, it's going to be up on the right, down on the left. If this were a minus x cubed, then it would be down on the right and up on the left, just the opposite, like that, because we have a minus x cubed here. So it just swaps it right to left. And I just said those, and that's if you've got a negative sign, that means that number out front isn't negative, and it's going to be reversed. This is the x cubed or odd look. If it has minus sign outside, then it's going to switch and it's going to have these end behaviors. If it's even, if that number is positive, it's going to look like this, both ends going upward. If it's negative, then it's going to be upside down. They're going to be both going negative or down. So let's take a look at this. You want to do a real quick pause and see which one of these this suggests, and then come back. All right, you're back. Well, x to the fourth means you might have it like this, or you might have it like this because it's an even degree. But it's a positive one out here, so it's going to be this kind of end behavior. So look for which one has an end behavior like that. Well, there's only one. It has to be C. It can't be A because it's got a positive one out here. So this one's out. These are odd degree behaviors. Oops, this is a good one. This is an odd degree behavior, and here's your guy right there. Try this one. We've got a negative x to the sixth. This is an even, so either it opens upward or it opens downward. And the minus says, guess what, guy? It opens downward. And remember, because this isn't x squared, it's higher degree, it's also going to be a bit flattened where it turns around. So which one is this? First of all, it opens downward. So we're going to be looking at this. And the x to the sixth says this is going to be a bit flattened in there. It's hard to tell on that one, though. Next, how about this one? You've got an odd degree, and this is positive out here. So you know, roughly speaking, it's going to look like that. It isn't turned upside down because you've got a positive 3 out here. And which one looks like that? Well, it's not this one. That is going the wrong direction. This is an even degree one. This is an even degree one. This is your guy. Next, how about this one? These aren't too hard, are they? I hope. All right, what do you see? X to the seventh. That's odd. So the first thing you think of is, hey, there's an odd one. But hold on. It's a minus x to the seventh. So we're going to have to turn that thing upside down. It's actually going to look like that instead. Or, excuse me, turn left to right. So which one is that? Well, obviously, this one. That's even, we had an odd. That's even, we had an odd. This one would be one that has an x to some power. There was a positive number out here, like a 4, for example. So D is your guy here. So here are some points that tell you about the characteristics. All intercepts, x-intercepts, are zeros, solutions, and so on. The behavior of the graph at these zeros is what you'll be looking for. Find the x-intercepts, see what's going on at those zeros. Is it going upward, downward, and so on. Find the y-intercept, because it's easy. Just set x equals 0, you got your y-intercept real fast. The sign of f of x in those intervals. So take a look at where the zeros are. Let's take a look at a number line. We're going to leave the y-axis out of it. Suppose we've got zeros here, and here, and here. The question in number 3 is, what's happening in these intervals? What's going on here? Is it positive or negative? In this interval, is it up here or down there? In this interval, is the graph up here or down there? And you've got a 4th interval. Is the graph up here or down there? How can you tell? Well, this is really easy because all you need to do, let me change the color of the cursor for a moment, if I can find this thing. There we go. I'm changing color to blue. So go back here. Where's my cursor? There we go. Okay, so how do you find out what's going on from here to here? Well, it's very simple. Pick any number you want in here. Let's call it A. Put that A in your function and see whether you end up with a positive or negative number. If it's positive, then the graph is up here in that interval. If the function value is negative, then it's down here somewhere, and that helps you graph it. Find f of A, and A is just any number at all in that interval. Let's suppose we pick this number in that interval. Just find the function value at B, see whether it's positive, that means you've got points up here in that interval, or whether it's down here for your f of B, and it's negative in that section, that interval. Same thing over here. Pick some value C, any value C in there. Find out whether C is positive, which means the graph is up here, or negative, and the graph is on the bottom. And last of all, pick any number out here. You can pick 1,000 or a billion if you want to, because it goes to infinity anyway. So pick a number D, find out what the function value is, and you can see whether the graph is going to be above the axis or below the axis, depending on whether this is positive or negative. Number 4, make sure when you're graphing it, you show, or graphing even on your calculator, make sure you show enough of the domain, and that's the x's, so you can see the end behavior. If your graph looks like this, you might not see enough of it. You need to see more of it. If you're doing it on the calculator, you're going to have to change that. We're going to ignore that phone. Moving on. Next. Okay, graphing it. The degree. There. All right, back to graphing a polynomial function. If this is your function up here, and I'm going to go back to red again. There we go. Go back to red so you can see it real easily. So here we go again, just checking. So here's your function, and it's in order as you'd expect. If it's degree n, and of course you pick that from up here, that's your leading term. Step 1, find the x-intercepts, also known as the real zeros. Another way of putting that is, set the function equal to 0 and see what x's make that true. Step 2, find f of 0. In other words, you're finding the y-intercept. So put 0 in for x this time and find out what that coordinate is. That's going to be very easy. But it does give you the y-intercept, and there will only be one. That's good news too. Whereas you might have several different real zeros or x-intercepts, you can only have one y-intercept because it's a function. Step 3, look at the end behavior. And you can tell the end behavior by what you've got here. If this function is of even degree, you've got one situation, and depends whether this is positive or negative. If this is odd, you've got a different situation, and the coefficient being positive or negative will change your graph. So let's take a look at this. How does this go? 2x cubed plus 5x squared minus x minus 6. Well, remember the possible rational zeros? All the factors of 6 are what could be your p-values in your rational zeros. The factors of 2 are the possible values for q in your possible rational values. Here's a list, because 6p could be 1, 2, 3, or 6, and it could be positive or negative of each of those. For the q, it has to be a factor of 2, which means you could have positive negative 1, positive negative 2. And put together all of these combinations in fractions looking like p over q. Some of them might be duplicates. That's all right. Throw them away. Try those using synthetic division. Remember, that's the easy way, especially with these integer values like positive negative 2, positive negative 3, positive negative 1, positive negative 6, missed that one. Now these two might be harder, so you might want to try the integers first and see what you get for zeros. And this one suggests why not start with 1? 1 is easy to work with, go with that. See if you get lucky with that one. If not, throw it out, try negative 1, and so on, until you get ones that work. We've done that before. Here's a synthetic division. One more time. Just bring the 2 straight down. This 2 times 1, there's your 2. Add those, you get the 7. 7 times 1 again, there's your 7. Add these, you get a 6. 6 times 1 is 6. Add those together. Hooray! You've got a remainder of 0, which means this is a 0. That also means that x minus 1 is a factor of this function. And it also means that that function is going to look like this. You found that that's a factor. And if you look at the bottom of the synthetic division, remember, this is the constant, this is the x term, this is the x squared term. So your second term would be 2x squared plus 7x plus 6. And you should be able to factor that. If you can't factor it, use the quadratic formula. So, step 1, factor that out. We've figured out by scientific or synthetic division that this is a factor because we had a remainder of 0. We got this in the synthetic division on the bottom row. And we can factor those pretty easily. And you now have the zeros of f, the x-intercepts of f. At 1, negative 3 has, and negative 2. And notice also that those 3 numbers split the number line into 4 different areas. Real quick like, throw 0 in there, 1 is somewhere in here, negative 1.5 or 3 halves is about there, and negative 2 about like this. Those three zeros, or x-intercepts, split the number line into this interval, this interval, this interval, and this interval, and that interval. We've got, oops, not that one, from here to here. There we go. We've got three x-intercepts, so we've got 4 different intervals. See what's going on. Check with a random number in this interval, say -4. Put that in the function, see if it's positive or negative. If it's positive, then the graph is somewhere up here. If it's negative, then the graph in this interval is down there, and so on. Remember, these zeros, or x-intercepts, are where the graph is crossing the x-axis, or touching it. And remember, the y-intercept is very easy, so that's an easy point to find. 0, -6 right there. You've already got the x-intercepts. You can graph those. The y-intercept is very easy to find. And that should also give you an idea of where that graph might go. Because if you've got 0, -6, how is that graph going to get from 0, -6 up to 1, 0? Well, it has to go up, right? So in some fashion, it's going to climb to 1, 0. On the other side, somehow it has to get to -3/2, 0. So somehow it's going to get up there between these two. Since it's passed, it's probably going to go up like this and down again. Now that's very general, but it gives you, I hope, a fair idea of what's going on with that graph from that function. Now how about step 3? What's the dominating term? What's happening on both sides? Well, we don't know yet, but if we look at this, the 2x cubed, what does that suggest? Let's slip back here. We have the 2x cubed. The x cubed means we're going to have something like this on the right and something like this on the left. The 2 just means it's going to be stretched out. But this is the end behavior. And we've got some points in the middle. So this helps us put it all together. Oops. Go forward here. There we go. We've got the dominating term is 2x cubed. That's the leading term. Each 0 has a multiplicity of 1. That means there's only one of them. So across the x-axis at each of those zeros, or x-intercepts, sketch either end of it with the end behavior, which you found from the first term, and then try to smooth things in the middle. And there you go. Here are the x-intercepts. Oops, not that. Here are the x-intercepts that you found. Here's the y-intercept you found, and the end behavior on this side, the end behavior on that side. All of a sudden, you have an idea of what the graph looks like. To really get an idea of what it looks like, get some extra points in those intervals, and that'll help you smooth it all in. And that will also tell you whether it's above or below, which keeps you on track. So here's an example of some test points that someone else used. Notice that this -3 is in the first interval, -7/4 is in the second interval, 0 is in the third interval, and 2 is in the fourth interval. Just put those values in here where the x is, and use the function to find out what you've got. In this case, this is what you get. That's obviously negative. The graph is below the x-axis there, above the x-axis here, below and above. There's your sketch. A good look. And remember down here, these we got from the zeros. The zeros give us the factors. Now how about this one? Well, we know right away what the x-intercepts are going to be, because we can just take each one of these factors and set it equal to 0. So x minus 1 equals 0, x equals 1. That is A0. A0, not 0 itself. The x minus 3, set that equals 0. 3 is another 0. X plus 2 equals 0. X equals negative 2. Another 0. We've got 3 zeros. Notice, though, this one has a multiplicity of 2. And that's going to be special for this function. Plot the x-intercepts. That should be easy. We get the points, which this, and this gave us. There's one, there's another one, and another one. So all you need to do, this will give you, f of 0 will give you the y-intercept, which you'll get down here, a negative 12. So plot that and your x-intercepts, and there you go. You can see the dominating term. Now the easy way is, when this is expanded, you're going to get an x squared. When this is expanded, well, it isn't expanded, you just got an x. So x, you've got 2 x's from this one, another one, another one, 4 altogether. So this is going to be in the same family as x to the 4th, or an even function. But notice you've got a minus out front, so instead of looking like this, squared off a little bit, it's going to be, it's going to be just like that. A little bit squared off in there. It's going to be headed downward because of that minus sign. And the end behavior is going to be down and down. We've got all those points and the end behavior. That tells us what it's going to look like. And it helps too if you do some of this before you use your graphing calculator. That way you have an idea what it should look like. And if you type your function in incorrectly and it looks strange, then you'll know you made a mistake. You go back to y equals on your calculator, make the adjustment, hit graph again, and you get a good picture. Okay, and that's a good picture for sure. Notice they've got some extra test points. So get a test point somewhere back here, a test point in the middle here, a test point in the middle here, and a test point somewhere out here to see whether they're above or below the x-axis. Smooth it in and you've got a good graph. So the factored form will look like this. 2 multiplicities of 1 and a multiplicity of 2. Again, the picture. Remember, you can find the value of a by substituting in the x and y values with that factored form. And then you can just solve for a. We've done that before, like this. So you pick an x. In this case, you could pick 0 if you wanted to. Put 0 in for those x's. Solve for a, like this. So you've got a -1 here, -3 there, and a 2 there, which gets squared. So you have a times -1 times -3 times +4 for a total of 12. So that -12 that you got from here equals 12a, and a equals -1. So now you can take this, put it into here, and you've got the function that you were talking about. So a few things to keep in mind. The x-intercepts are places you want to find. You want the zeros of the function. You want the solutions of the function, the factors. All of these go together. When you're finding the x-intercepts, you're finding the zeros, you're finding solutions, you're finding factors, all at the same time. All four of those are different facets of the same characteristic of the function. And you can read through this. We're talking about polynomials. If a is an x-intercept, it crosses through there. So x equals a will be one of those. And that also means since x equals a, x minus a is a factor of that polynomial. Remember, we're talking about a polynomial that has real coefficients. No i's, no complex numbers. No complex numbers that have imaginaries, let's say. Now, this is called the intermediate value theorem, and it sounds exotic, but it really isn't. Let's give you a quick idea what this means. So, somewhere here, there's a number a on the x-axis. Somewhere here, there's a number b. Now let's suppose the function value for this one is there. So the graph is going from here, other places. B, let's suppose the function value b is there, below the x-axis. The intermediate value theorem says that to get from here down to here, somewhere you have to cross the x-axis. So you can't get from here to here without crossing the x-axis somewhere. So there's at least one real zero between a and b because it has to cross the x-axis. All right, we're finally getting toward the end. Let's see. We use synthetic division in a graph to show that this one has a real zero between 2 and 3. So real fast, we're talking about x values of 2 and 3. Very quickly, you want to find f of 2 and f of 3. If those are a different sign, then there's a 0 somewhere between 2 and 3. So we can take this 2, use synthetic division, and that gives us the function value at 2 is a -1. So roughly speaking, that means somewhere here at 2, you've got a point in your graph like that. F of 2 means 2, -1. Now how about the 3? Do it with 3. What do you get? You get a 7. So over here at 3, you get a +7 like this. Now we're going from 2 to 3. how do you get from here up to here? You have to cross the x-axis. There's no way around it according to the intermediate value theorem and logic too. You don't know what it is perhaps right now, but there has to be one somewhere. So here we go. Here's a graph. There's 2 is somewhere like that, and 3 is somewhere like that. So somewhere between those two, you cross the x-axis. And it looks like it might be, I don't know, 2 point something anyway. And if you try that with your calculator, you can hit trace, for example, trace. And you can move your cursor along this curve until you find the place where it crosses the x-axis. And while you do, when you get there, it's going to say that the function value is 0. That's what you want. And this will tell you what your 0 is, what the x value is. That's a solution, or you've got the picture, your solution or your root. So approximate the real zeros of this one. Remember, we can make a list of possible ones. Let's see, what's the end behavior? Well, because this is x to the 4th, that's an even one, and it's a positive x to the 4th, so this will be the end behavior up on either side. So we know what's happening on the far left and the far right. What's happening at 0? That's easy to do. That wipes out all these x terms. F of 0 is -1. That's easy. That gives you an extra point. So you've got the end behaviors, and you've got this point. And if we want to approximate the zeros, we can use the graphing calculator use y equals, put your function in, hit graph to see it, and use trace and see where those zeros are. Here's our function, x to the 4th. Well, better to look up here instead. It's hard to see that calculator version. And you can also get a table version too, with some numbers in there. I'll let you do that. All right. We don't get a great degree of accuracy, but we get pretty close sometimes. So the other 3 zeros, here, here, and here. Got 4 zeros. 1, 2, 3, 4. Remember back here, this is an x to the 4th, so it's going to have 4 roots, 4 solutions, and we've got 4 there. And you can see it on the graph. It crosses the x-axis 4 places. Now this is an interesting one, and I don't really want to do this online like this. Instead, ask in class how to do this. In class, it'll be easy to explain. Just to give you an idea, one of the things you're going to do is you're going to hit the stat key on your calculator. Then you're going to choose one, which is called edit. And what you're going to do is you're going to put these numbers in. And for the x's, list 1. That's first in this table that you'll see. List 1 is here, list 2, list 3, and so on. in the list 1, you're going to put the x values. Now, these numbers for the year are rather large, so to get a better picture, we're going to let x of 0 represent the year 2000. So in our list 1, we'll have 0 at the top, sort of like this. Here's list 1. 0, 1 for 2008, 2 for 2009, 3, 4, 5, 6, 7, 8, 9, 10, 11. All 12 of those. Notice there are 12 years here. So x's from 0 to 11 will represent years 2007 to 2018. Once you've got those in, double check, make sure you didn't make any silly errors. Cursor to the right to get to list number 2. List number 2, you're going to have to line up carefully. Right next to the 0, you want 2.7. Right next to the 1, you need 2.88. Down here next to 2, you need 3.17. To the right of the 3, you want 3.25, and so on. Put all those in and have them ready. Bring them to class, and we'll go on from there. Because what we're going to do is we're going to come back in when you've got this done, and the calculator, even if you turn it off, will keep that. What you'll do next is you're going to hit Stat. And from here, this time instead of Edit, you're going to move the menu to the right, and one of your options is Calculate. That's the middle option, the one in here. And when you hit the Calculate menu, we're going to try a couple of different things. And that's what I'm going to do in class. You might be able to figure it out yourself, but I have some extra things I'm going to tell you. So this is pretty much what I mentioned. The first thing you're going to do is you're going to find the regression equation, an equation that matches up the years with the price. How could you take a year, for example, and estimate what the price is without knowing it? Well, I've got some clever ways of doing that, and you're going to first try to find out what that equation or function would be as a quadratic. There's a graph of it, and this is a scatter plot, they call it, of the 2007 was here, 2018 was here, yeah, that's right. And this is a graph. This is an idea of what that thing looks like. And this tells you what that function is. Now it's a little bit elementary. It tells you what kind of function you've got. This is a quadratic because you see the x squared, and it doesn't have room to put all the rest in. So it just tells you what the a is down here. It tells you what the b is down there. It tells you what the c is. And it also gives you some other information. It tells you r squared. And the closer this is to 1, the better your model is, the better your function is. Now that's with a quadratic. You're going to do it next with a cubic function. And those are what you get with a cubic. You'll also try it with a quartic function. Notice that the quartic actually gives you the best model or the best function for those numbers. All right, so I'll fill in the rest of it in class. Just make sure you don't forget. I'll even go over how to put it in the calculator too, the whole thing. And that's just a wrap up. The R squared values, excuse me, will tell you what's the best choice for your model. Because you want a model. The model that says if we have a year, what's the estimate for that year? And that's it, folks. I'll see you next time. 3.5. Take care.